Hi everyone, my name is Dagny, and today I'm going to present an analysis of the Golden Gate Bridge. Let's jump into it. So, the first thing I want to do is estimate the thickness of the main cables on the Golden Gate Bridge. To do this, you need to understand a little bit more about suspension bridges. First, there are main cables that run along the length of the bridge. These are thicker, and then you also have suspender cables, which are vertical, as you see here in the picture. Another thing you should know is the term sag. This is simply the amount that the cables actually sag down from the towers, so it's that vertical distance measured there. And thirdly, we have the span of the bridge, and that's simply the distance between the south and the north tower. To approach this problem, I want to break it up into 3 steps. First, determine the weight supported by the main cables. Secondly, calculate the tension in the cables. And thirdly, estimate cable thickness based on tension and material strength. So, first of all, to determine the weight supported by the main cables, I approached this by doing some research and finding out what the weight of the deck would be. So that's 330 kilonewtons per meter, and then we also have the weight of the vehicles and the weight of the cables, which are each 0.87 kilonewtons and 48.7 kilonewtons, respectively. So that brings us to a total weight of 379.57 kilonewtons per meter. But since we have 2 cables that run along the length of the bridge, we then need to divide by 2, as shown here, to get 189.785 kilonewtons per meter. Just to do a quick recap, this distance is the sag, and it's 144 meters, and then the distance between the 2 towers is 1,280 meters. So secondly, to determine the tension in the main cables, we can now look at the physics a bit more. So here, we're just looking at half the bridge, and we're summing the moments around point A. To find the tension in the main cables, we want to find the horizontal tension as well as the vertical tension. So the horizontal tension, many engineers make the assumption, is constant along the entire cable. Especially in the middle, which we call the midspan, it's only horizontal tension and no vertical tension. So to go about finding the horizontal tension, we can sum the moments around point A and say that that is in equilibrium, so it equals 0. We then find that the horizontal tension is W times L squared over 8 times the sag distance. So then we find the horizontal tension is equal to 269.92 meganewtons. And then we find that the vertical tension is 121.462 meganewtons. To then calculate the max tension, which almost always occurs at the top of the tower, we then find that the max tension is 295.992 meganewtons. So then moving on to the last part of the problem, to estimate the actual cable thickness, we use this equation here, which is A equals T max over the stress, and then we use D equals 2 times the square root of A over pi. Just simple math there. So then, since we know that the cables are made from galvanized steel, which typically has a tensile strength between 400 and 600 megapascals, we can use 500 megapascals just for simplicity. We find that the diameter is actually equal to 0.9 meters, which is very close to the actual real diameter of the cable, which is 0.92 meters, shown on the right. It's probably an underestimate that we calculated just because we haven't factored in the safety factor yet. Lastly, to look at another aspect of the problem, kind of an add-on, if we were to change the original cable so that 7/8 of its original diameter, how much taller would the bridge towers need to be? Assume that the sag changes the same amount that the tower height increases. To do this, I kind of backtracked, so I found out what the new area of the cable would be, and then I found the new tension, the new max tension, would be 226.57 meganewtons. And then I found that the horizontal tension would then be slightly lower at 191.27 meganewtons. And then from that we can find the new spanning distance, which is 203.2 meters, which is 59.2 meters higher than before. So you can see that a small change in the diameter will really increase the sagging distance. Thank you.